All right, so how do we Laplace transform a derivative? Well, we go to the definition. Anytime we have something new, we always go to the definition. And so if I have a derivative, I'm going to use that definition of integral from 0 to infinity. Got a little background noise, so if your mic's on, will you please just mute it for now, and then when you want to ask a question, unmute. Thanks. So integral 0 to infinity e to the minus st f prime of t dt, because f prime's the derivative. So if we can figure out how to solve this, we will know how to Laplace transform a derivative. Well, our variable of integration is t, and we've got two different factors or functions that involve t. We've got this piece and we've got this piece. So I'm going to do an integration by parts. So remember, integration by parts, it's going to come in handy here because when you're trying to integrate a product. So I'm going to call this one u and this one dv. So remember, we integrate by parts, we have u, that's going to be e to the minus st, and we have dv, that's going to be f, don't tell me my pen's acting up again, f prime of t dt. If anybody knows how to cure a pen that does that, it's never done that until like this week, so I don't know what's going on. Okay, so now we need to figure out the v and the du, and remember our integration by parts formula. So if I integrate that, v was just f of t, and if I differentiate that, du would be negative s e to the minus st dt. If we remember our integration by parts formula, I'm going to put it up at the top here. Remember, when we integrate u dv, it's uv minus integral of v du. I was going to do that all day. Du. Okay, so I just need to now apply that. So I need uv, so that's these two guys there at the top. So that's e to the minus st f of t, and that will need to be evaluated from 0 to b, and we'll put the limit on here as b goes to infinity. And then I have minus the integral of v du. And so v is f of t, and du is negative. Let me just put the du first, the first part of it here. E to the minus, let's see, minus s e to the minus st, and then we've got our f of t and dt. All these annoying things here. Okay, so this is still from 0 to infinity. We'll just put for this part of it right here. Okay, so as we're kind of looking to see what we have, I'm going to do a few things to this. The first thing I'm going to do is combine this negative and negative and make that a positive. I'm also going to bring the s out in front of the integral. Now, why can I do that? Because my variable of integration is t. So if I'm integrating with respect to t, you treat s like a constant. So I'm going to move it out in front because I'm trying to figure out what I have here for this. And so the next thing I'm going to do is go ahead and start writing it, doing the evaluation piece. And so I've got limit as b goes to infinity, and it's e to the minus sb f of b minus e to the 0 f of 0. So that's kind of the first piece of this. Now, looking at the second piece of this, I have a plus sign and I have an s, but if you look at this piece right here, that is nothing more than the Laplace transform of the function. That was the definition, okay, that of the Laplace transform of the function. And so this part is just the Laplace transform of f of t. All right, so let's go ahead and figure out as b goes to infinity here. So this will be just a constant, a number, whatever f is as b, but b is going to infinity, but it's just evaluating it at some specific place at some instance. And so this will be the thing that dominates. This is going to go to 0 because we're going to have s greater than 0, and so this is a negative exponential. So this part's going to go to 0, and then e to the 0 is 1. So let's write down what we have, and I'm going to turn it around and put this piece first, and then I'm going to put this piece next. So we have s times the Laplace transform of the function minus the function's initial value. And that's what we got when we Laplace transformed the derivative. So this is what we're going to do when we need to do that. We're going to take s times the Laplace transform of the function and then minus the function value at 0. And this is often written in Laplace's world. Once you transform f of t to show you're in Laplace's world, you use capital for the function, so I'd use a capital F, and you use s for the independent variable. So I could write this as s, f of s minus, and I still need this f of 0, which is just going to be a number. So this just means the Laplace transform of the function f of t. So we now have a formula for how to transform a derivative. So this is just kind of an existence thing that says if it is of exponential order, remember that meant you could bound it with an exponential function, and that the derivative exists and is piecewise continuous on 0 to infinity. So it can be completely continuous, but it's going to exist also even if it's piecewise continuous. Then the Laplace transform is given by this formula that we just found. And so this is typically the way that I remember it, but bottom line, it also incorporates the initial value. So now let's see this in action with the differential equation, and that'll make some sense. So basically this is what we're going to be doing. We're going to take the Laplace transform of the differential equation that we want to solve, and we'll substitute in the initial conditions, because right here we already have that it needs an initial condition on it. We're going to see second order and higher in a few minutes, but this will be our steps. Then the resulting thing, once it gets transformed, will have capital function values. So if our differential equation had y prime, we're going to have a capital y of s in Laplace's world. Anyway, we're going to algebraically solve for that. So we are going to get the y of s by itself, and you're going to see how that works in just a minute. And once we do the algebra, and it's going to involve partial fractions a lot. You'll see kind of why as we go to do them. Well, you got to see a few things in the end part of 8.1's homework. But anyway, once you get the y of s by itself, then we're going to take the inverse transform. And if you inverse transform y of s, it comes back as little y of t, which is our solution. And it'll already have the initial values incorporated, and it'll be done. So let's see how it works. Start with an easy one. This is something we definitely would not want to Laplace transform, because you can just integrate both sides and get it solved. But we're going to do it anyway because we want to learn the process on an easy one first of all, and then we'll start applying it to other things. So the way you do it is you take the Laplace transform of both sides and you incorporate the initial values. So the Laplace transform of this is the same thing as y prime, so we can think of it however we want there, but Laplace transform then is s times the Laplace transform of y. So I don't know what that is, so I write it y of s, because y is our variable there, and then I have minus y of 0, so I'm just doing this piece right here in the formula, but ours is y instead of f. So, and then it's going to equal the Laplace transform of the other side. And if we remember how the Laplace transform of t was 1 over s squared. So that, and then we incorporate the initial value, and then we will be in Laplace's world. Okay, so the initial value y of 0 is 1, so that's a 1. Okay, now we're in Laplace's world. All functions are capital letters. All of our independent variable is now s. We're going to algebraically solve this now then for y of s. So we're going to get this by itself. So the first thing I'm going to do is add 1 to the other side, and that will take care of this piece. And then I need to divide everything by s. So y of s is going to be 1 over s cubed plus 1 over s. So I divided the other side by s, and I just did it to each term. Okay, once you have y of s by itself, you're ready to do the inverse transform to bring it back into our world, and it will be the solution. So what I'm going to do is take the inverse transform of both sides. Whoops. Okay, so I would then do this. Laplace inverse transform of both sides. Well, when you inverse transform y of s, it's y of t, little y of t. And when we inverse transform the right hand side, you can inverse transform each term and then add them together because it's a linear transformation. So we're going to split it up. So trying to bring this one back, 1 over s cubed, well, we knew that 1 over s was 1 and 1 over s squared was t. T. And then remember, it went 2 over s cubed was t squared, because how it works in general is it's the n factorial. So if you wanted it for t to the n, it's n factorial over s to the n minus 1. This is the Laplace transform of some power of t. So in looking at mine, I have 1 over s cubed, and that's not what I want. I want 2 over s cubed. So I make it 2 over s cubed, but I need to compensate for that fact. Now this piece will come back then as a t squared, but it's going to have the 1/2 on it. So it's going to be 1/2 t squared plus, and then the inverse transform of 1 over s, that's just 1. That's just 1. So that's my solution. And I did it the hard way as far as Laplace transform it, when we could have just directly integrated it, but it was so we could, on an easy one, see the process. Let's go back and look at it. I could have just integrated both sides with respect to t, and so then I would have y equals 1/2 t squared plus c when I directly integrated, and then if I did y of 0, that would be c equals 1, and so there it is. So that's on an easy one, but we've got the process. Any questions on sort of the process or what I did? That's essentially the plan, is transform it, algebraically get y of s by itself, inverse transform it. Okay, everybody's still out there and awake, right? Okay, no questions. All right, so of course we want to know what if it's second order, because a lot of our differential equations we had were second order. So what we're wanting is the Laplace transform of a derivative, a second derivative. Well, we're going to use something we know, something we just found out. We can rewrite this as the derivative of the derivative. I mean, if it's take the derivative of f prime and you have f double prime. So now I can use what we just found out, and instead of putting f in it, I'll put f prime in it. We knew that the Laplace transform of a derivative was s, and then times the Laplace transform, it was the function, but it's going to be the function prime now because that's what's there instead, and then minus, okay, and it was the function at 0, but it's going to be the function prime at 0. So in other words, that's just the very equation we just had, except where the f's were, they're f primes. But now I need to take that and do one more substitution, because I want this to be just in terms of f. So I'm going to write that down here. So I'm just going to replace that with the formula again. The formula was, if you want to Laplace transform f prime, it was s times the Laplace transform of f, and then minus f of 0. And then this piece is still on the end, f prime of 0. Okay, so putting kind of all of that together so we can kind of see the pattern and a formula, this is going to be s squared, and I'm going to write this as just f of s. Okay, minus s f of 0, and then because we had to distribute that s through, and then minus f prime of 0. So if it's second order, it's going to have a squared on the s, it's going to have an s on the first initial value, and we need a second initial value to determine a unique solution. We need to know, remember we learned that for second order, a function value and a derivative value at some initial point. So that's our formula. I just wrote it with the capital F of s, or you can write it as the Laplace transform symbol, but that's our formula for a second derivative. So s squared, and then s initial value, and then the initial value. So then we're going to be interested in what if it is higher order than that. So we want a general formula kind of looking for the pattern, and so we could try Laplace transforming a third derivative, and I could do that by Laplace transforming the second derivative as a derivative and using the derivative formula. So similar to what I just did, and you can probably see what the pattern would be, because that would be s in there, and it would give me another s in there, and so bottom line it's going to be s cubed times the Laplace transform of s, and then it's going to have an s squared times the initial value of the second derivative, and then it would have minus an s times the first derivative, and then it would finally have on the end the initial value like that. This will generalize as we keep taking derivatives, and so this is what it's going to look like. If you want to Laplace transform an nth derivative, so any given one, it's going to be s to that power, and the Laplace transform, and then this is going to have the, I got these backwards, because think about when I do them, this was the starting with the 0 and then they increase. So sorry, I didn't have these right. Got to be in the other order. You start the initial values and then you increase. When I do this, I usually say it in my head, and then I can keep it straight. Let's see, let's make sure I got it right now. N minus 1. Okay. Okay. Yep, that should do it. Okay, so if I'm working on this one and I look at the pattern, basically I have that s to the n, and then I have each of these initial values, and the first one is just f of 0, and then you start with a derivative. The first derivative, the next one would be the second derivative, dot dot dot, up to 1 less than whatever our differential equation's n was. That's why it's the n minus 1 derivative, because you need, if you have a third order, you need 3 initial values, f of 0, f prime of 0, f double prime of 0. And if you had an nth one, you need n initial values, f of 0, f prime of 0, double prime, and up to 1 less than whatever the n was. So it will generalize, so we're going to be able to apply it to any type. So now let's just see, we're going to spend most of the rest of the time applying this because it's a lot of work and you need to see some examples to kind of see how to do that. And then we've got a couple other things to throw in there that you need to know that can come up along the way. So let's start with a second order differential equation. and we would need the two initial values. So I'm going to take the Laplace transform. This is homogeneous to start with, and then we'll do a non-homogeneous. So I'm going to take the Laplace transform of both sides. So this first one, the second derivative, is going to be s squared. Now I need the function, and so it's going to be y of s stands for the Laplace transform of y. And then I have minus s f of 0 minus f prime of 0. So all of that is the Laplace transform of the first derivative. It's just this equation here at the top. Okay, so now I have plus, and I now need the Laplace transform of y prime. That was s times the Laplace transform of y, which is capital Y of s, minus the initial value. And then I move over to the next term, and it's minus 2, and I need to Laplace transform y. So that's capital Y of s. And then equals, and we haven't talked about the Laplace transform of 0, but it should be pretty obvious what it is, because the transform is e to the minus st. You put the function right here, dt, and if you put 0 in here, then you're integrating 0, and it's 0. So that's 0 in our world and in Laplace's world. Okay, after you get the make the transforms, you use all of the initial values. So y of 0 is 1, so that's a 1. Pen. Okay, so that's a 1. So I'm just going to cross that off, and we have this because it's times 1. F prime of 0 is 4, so that's a negative 4 in there. I included the negative sign. So okay, and then y of 0 was 1. I'm just going to include the negative signs down there on these guys so I don't lose them. Okay, so I put all of the initial values in, but let me rewrite what I have now so I can clearly see what I've got. I've got s squared y of s minus 4 plus s y of s minus 1 minus 2 y of s equals 0. Okay, so that's what we have in Laplace's world, and we're going to algebraically solve for y of s, so get it by itself. So bottom line, we're going to take everything that's a y of s term, and we're going to factor the y of s out. And you typically do it, factor it out on the end just because you're solving for it, but it doesn't matter. So I'm going to have s squared plus s minus 2. Those are all on the y of s, and so I factored the y of s out of those 3 terms, and then I'm going to move the other terms to the other side, so that's going to become s plus 5. So I moved this negative s over, and then I had negative 4 minus 1, which is negative 5, and I moved that over to the other side. So I'm algebraically getting y of s by itself, and you can see it's almost by itself. And so now I can just divide by that s stuff and have y of s by itself. So I'm going to divide s squared plus s minus 2. Now y of s is by itself. And so now I need to inverse transform. And when I inverse transform, and that's the hard part, but when I inverse transform, it'll come back and it'll be solved. So I don't even think of it as solving a differential equation, but I did because the Laplace transform involved an integral. Its definition has the integral in it. So I undid the derivative in disguise by doing the transform. It wasn't obvious, but that's why it would work. Now I need to get it back. So the first thing I'm going to need to do is factor the denominator, because I've got to get this recognized as something I can inverse transform. So this is going to be s plus 2 and s minus 1. And so how would I inverse transform that? That's one of the reasons you had a few on the homework to practice. So when you see them in a differential equation, that right-hand side is going to be the hard thing to inverse transform until we've learned a few little tricks. So any suggestion is something I can do to get this recognizable to inverse transform?
Partial fractions.
Yep, you're going to be doing partial fractions a lot because it's going to be common to have some stuff on the side and divide by the other stuff just like we did here. So we're going to do partial fractions. So we got s plus 5 over s plus 2. I'm doing it down in the corner. S minus 1. And so that's going to be sum a over s plus 2. So you'll remember everything you knew about partial fractions by the time we're done. We did them in college algebra, you did them in Calc 2, and we're going to be doing them a lot on this section. So remember what you do is you clear it of fractions. So s plus 5 equal a times s plus 2 plus b times s minus 1. And then if it's not got quadratic factors, which this doesn't, they're linear factors, we do the convenient, in this case it's an S, convenient S method. So I'm going to let S be 1. That's going to let me find A. So I put a 1 in. So I have 1 minus 5, which is negative 4. And added other lines. There we go, negative 4. And then if I put a 1 in, I have, let's see, hold on, that confused me. I did something wrong. What have I done here? Let's see. Oh, I wrote that as a minus, and it's a plus. I knew it wasn't right because I worked it before and it was even then, so I knew something was fishy. Sorry, I can't copy down to the bottom of the screen there. So let's try again. So I put a 1 in, so that's 6. Put a 1 in for S that's here by the A and add it, that's 3A. And of course the 1 in by the for the S by the B made it 0, so that's why we picked it. Okay, so A is going to be 2. Now let's let S equal negative 2 so we can zero out the A term and figure out what B is. So if we put in negative 2 plus 5, that's going to be 3 on the left hand side. Negative 2 will zero out the A. Putting a negative 2 in for B is negative 3B. So it looks like B is negative 1. Okay, so we've got our partial fractions, and so we're going to rewrite our right hand side. I'm just going to rewrite down here, so it's going to be y of s equal, and so we can rewrite the right hand side as my a was 2.
So when you did the partial fractions, when you went from the fraction to the not, you had s plus 2 with a on both of them.
Oh, I did it wrong. Yep. Shoot. Okay, so
You could just
let's just switch these. Yeah, I did it. When you clear it of fractions, what it does, thank you. I have that incorrect. So let me fix that. So I'm going to leave this one as the 2 and the minus 1 and just change them here. So so this will be the s minus 1. Thanks. You caught a mistake I made here. And so I would have caught it in a minute because I'd have got the wrong answer, so I appreciate you pointing that out. So what you're doing actually, and let me just write out what you're doing. You'd tend to do it in your head, but had I written it out I wouldn't have screwed it up. What you're doing is you're multiplying both sides by the denominator so that you can cancel all the fractions. So it cancels on this side, and here you have s plus 2, s minus 1, and it cancels that one, and then here you have s plus 2 and s minus 1, and it cancels that one. So see, I had them backwards. I just wrote it in a hurry, and I put what was supposed to be in the denominator on the top, and the denominators cancel and gives you the other piece. So thank you I appreciate that, pointing that out. So now that I swapped the denominators, I'm okay, and so my work here is okay. So now let's go ahead and do the right thing here, though, because that's going to matter. I would have had them backwards here and would have gotten it wrong. So okay, so let's redo that, and let me just make me a spot right here that's away from all my, sorry, I'm trying to work on, this is like working on a little small whiteboard, same issues. Okay, so it's going to be y of s equals, and so our A was 2, and that's over S minus 1. Okay, and then our B was minus 1, and that's over S plus 2. Okay, and so now we're ready to inverse transform because I can recognize both of those and it'll come back as the solution, including already taken into account both of these initial values. So inverse transform y of s, that becomes y of t. And inverse transform 2 over s minus 1, well, we know that 1 over s minus a comes back as an exponential. The 2 is just a constant out in front. So it's going to come back as 2e to the t because a is 1. So 1 over s minus a is e to the a t. So there's our first piece. And then doing our second piece has a minus. And so this is going to come back as e to the, so it's 1 over s minus a. So it's minus 2. So there is our solution. It was a lot of work, a lot of steps. I would not have done a homogeneous second order that factored with Laplace transforms because it's more work, but we want to start with stuff we know and then we'll build and then we'll be able to use it with stuff we wouldn't be able to solve. If I was solving this our normal way, I would have write the characteristic polynomial, and then I would have factored it to find the roots, which would have been r and plus 2 and minus 1. So I would have had e to the minus 2, which I have, and I would have had e to the t, which I have. But when I wrote the solution, I would have had to go c1 e to the minus 2t plus c2 e to the t, and then I would have had to figure out, the initial values to find the C1 and C2. So it still would have been some work, but not as much work as the Laplace transform. But when we have non-homogeneous, and particularly when we have a little bit crazier right-hand sides, the Laplace transforms are going to be the way to go. Any question on anything I did there? Okay, let's see another one then, because the way we're going to get good at these is see a few examples. Now this one is the same DE as this first one I did on the left hand side, but it's non-homogeneous now, and I think the initial values are a little bit different now, and that's fine. So let me just look. Yeah, so little bit different initial values, but a non-homogeneous. So we already kind of had Laplace transformed the left-hand side, but let's just do it again for practice because we should be able to start doing this. Okay, it's s squared because it was a second derivative, y of s. Then initial conditions, you start the initial conditions. You decrease the s by 1 and start an initial condition, and then you have, these are always subtracted, and then the next one would be start the derivatives on the initial conditions. So that was our y double prime transformed, and then we have plus s y of s minus y of 0, that was our y prime transformed, and then minus 2 y of s, that's the transformation of y there, equals, now this time we need to Laplace transform something besides 0. It's 10e to the minus t. So we know it's going to be 10 on top because we just multiply the constant later. And then let's transform e to the minus t. We know that's s minus a. So that's going to be plus 1 because it's minus a minus. So we've got the s plus 1 there. Okay, we've got it in Laplace's world almost. We got to get these initial values in. So y of 0 is 0. So this one's 0, so I'll just cross that off. Y prime of 0 is 1, so this is minus 1. Okay, this was y of 0 again, so that one was 0. So once we have those initial values, I'm going to group the ones that are y of s terms and factor out the y of s and move the initial values to the other side. So this is going to be s squared plus s minus 2 on the y of s piece, and the other side's going to be 10 over s plus 1, and then plus 1 from this initial value here. Okay, so I now have, I'm now ready to get the y of s by itself, and probably the easiest way to do the right hand side would be to combine it under one fraction, and then we will end up putting this other guy over there with it. Just trying to think which should be the easiest way. You can actually keep them separate, but then you'd have to do partial fractions twice. So I think it's worth getting the right hand side as one fraction first. So if we did that, it would need an s plus 1. So the right hand side is now going to be s plus 11 over s plus 1. Okay, that way it's going to be only one time we have to do partial fractions when we get this other piece over there with it. So let's get the other piece over there with it, and I'm also going to write it factored. Okay, we'd factored this before, and it was an s plus 2 and an s minus 1, and then we already had the s plus 1 that was already over on that side. So there it is. We got y of s by itself, so we algebraically solved for that. And now we've got to inverse transform, and that's where the work comes in, because you've got to get it into a form that's recognizable to inverse transform. So we're going to need partial fractions again, and this is going to be a bigger partial fractions because we have 3 different factors, but we can do it. Let's go ahead and do that. So I'm going to put it down here at the bottom. So I have s plus 11 over s plus 2, s minus 1, and s plus 1. And so the partial fractions are going to be a over s plus 2 plus b over s minus 1 plus c over s plus 1. Let's see if I can clear the fractions right this time. So we got s plus 11 equals, so basically I'm multiplying a by s plus 2, s minus 1, and s plus 1. And the s plus 2's cancel, so a is going to have s minus 1 and s plus 1 on it. And then we're going to have plus b, and the s minus 1's will cancel, so it'll have s plus 2 and s plus 1, and plus c. And on C, the s plus 1's will cancel, so it'll have an s plus 2 and an s minus 1. Okay, so there is the breakdown for the partial fractions, and so let's go ahead and conveniently pick some things so that we can find our a's, b's, and c's. And this will work with the convenient s method again, since they're all linear. So let's first of all I'll put them over here. Let's let s be, I like to do it in alphabetical order. I'm going to find a first, so I'm going to let s be negative 2. So if it's negative 2, s plus 11 will become 9. And then negative 2 will zero out the b part, and it'll zero out the c part. And I would be putting in negative 2 for the s right here. So negative 2 plus 1. And so when I do that, it looks like I'm going to get negative 3 times minus 1. So that's going to be negative 3a. So a is going to be negative 3. Now I'll let s be 1, and that will zero out except for the b term, so that I can find that one. Okay, so if I put
it would be a would equal 3, because negative 2 plus 1 is negative 1.
Okay, negative 1, you're right. Negative 3, I should have wrote it out, trying to work on it a little in my head. Thank you. So that would be 3a, so that would be a positive. Okay, thanks. I'm just double check on my notes over here. Yeah, I wasn't looking at them. I'd have picked up my mistake already. Thank you for picking it up. Okay, so now let's let s be 1. That will zero out A and C. Let's see if we can get it right this time. So 1 plus 2 and 1 plus 1. Okay, so putting a 1 in on the left-hand side will make that a 12. And so I should have, what, 6 on our B. 6B, because I have 3 times 2. So it looks like B is 2. Okay, and then I'm just going to erase these out of the way, and we'll go ahead and do the C right there. And so for C, to find C, we're going to let S be negative 1. Okay, so if S is negative 1. And so if I put in a negative 1 on the left-hand side, I'm going to get 10. And then that is going to zero out the A part and the B part. And I'm going to have negative 1 plus 2 right here. And I'm going to have negative 1 minus 1 right there. So it looks like that will be negative 2 on the C. So it looks like C ends up being negative 5. So lots of partial fraction work happens when you're in Laplace's world, so you can get it back to something that we can inverse transform. So let's write down how that broke down. So A was 3, so we got 3 over S plus 2. And then B was 2, so we've got 2 over S minus 1. And then C was negative 5, so minus 5 over S plus 1. Okay, so we are ready to bring it back and have it solved. And so we inverse transform y of s, and that comes back as y of t. And then the inverse transform of 3 over s plus 2, it's going to be 3. And this is s minus a, so s minus a minus 2. So this is going to come back as e to the minus 2t. And then we have plus 2. We're looking at this next term. That's going to come back as e to the at, and so that's going to just be an e to the t. And then the last one is minus 5 e to the minus t, because this is s minus a minus 1. Okay, so this is our solution, including initial values and so forth. Now let's think about it for a minute and see if it makes sense here. Can you identify which part of this is we know that when we solve, we have a homogeneous solution plus the particular solution. That's how we would have had to solve it had we not Laplace transformed it. And so we found out that those roots were negative 2 and 1 of the characteristic equation, and so this is indeed our y of h, and this is our y of p, because we would have guessed a particular solution up here, a e to the minus t. So when you inverse transform, it has the initial values already taken care of, and it has, like when we would have used method of undetermined coefficients, it's already determined that as well. So you see that we could have solved this a different way, but we'd end up getting that very same solution. So any questions off that? It's a good example of how to do a second order non-homogeneous DE with Laplace transforms. Okay, we want to do a couple more examples because different things are going to crop up, particularly in trying to get it back into our world. So those are some algebra things, but they're things that we need to definitely review. So, okay, so here's another initial value problem. We got a second order non-homogeneous one. So we're going to Laplace transform. So the second derivative is s squared y of s minus s y of 0 minus y prime of 0. Okay, so there's our first, that is the y double prime, plus 4, the Laplace transform of y is just capital Y of s, equals, and it looks like we got that same non-homogeneous piece, is going to be 10 over s minus a, and a is a minus 1, so it's going to become a plus 1. Okay, so that part looks very similar, but we have a different dE, and we're going to have some little different outcome here. So let's do our initial values. Y of 0 is 4, so that's going to become a 4, and y prime of 0 is 0, so that one is going to be out of there. Okay, the next thing we want to do is get our y of s's together and get our constants over to the other side. And so that's our next step. We're going to have s squared plus 4 y of s, and on the other side we're going to have 10 s plus 1 plus 4s. Okay, now this time I think I am not going to combine those fractions, because I won't need to partial fraction the second one in that case, because this is just one piece. So sometimes I'll combine them, so if I'm going to have to do partial fractions on both of them, I'll combine them first so I don't have to do two separates. Sometimes combining them would make it more work, and then I would just do partial fractions twice, or sometimes in this particular case I'd only need to do partial fractions on one term, so there's no reason to combine them. Okay, so let's write down what we've got. We have y of s equals 10 over s squared plus 4 times s plus 1. Sorry. Okay. And then I have plus 4s, and that's going to be over the s squared plus 4. All right, so now as I'm looking at this and trying to kind of see what I can do to inverse transform, I didn't get out of partial fractions, but I only need to do it on the first one. You could have also combined them, but I chose to do it a little differently this time, just to kind of show you some different approaches. All right, so let's put that down here. So I got 10 over s squared plus 4. This is going to remind us how to handle a quadratic factor in partial equations, or in partial fractions. And this is going to be s over s squared plus 4, and then I see, wait a minute, that's a quadratic factor. So remember, when you're setting up partial fractions, that you're going to need as plus b. So anytime the denominator is a quadratic that does not factor, you're going to need two terms in the numerator, an s term and a constant term. And then the other one is going to be c over s plus 1. All right, so now when I clear this one of fractions, I'm going to have 10 equal as plus b times s plus 1 and plus c times s squared plus 4. Now I can find c here because I could let s be -1, but then I don't have an easy way to find the a and the b. So you've got a couple choices when you had that quadratic factor. You can just choose some other values of s and find the a and the b, or you can just multiply it out and equate coefficients. And that's what I'm going to do here, because I want to remind you of how that worked when you did partial fractions. So how that works is you would need to FOIL this, multiply everything out. I'd have as squared plus bs plus as plus b, and then distribute the c through on the next one, cs squared plus 4c. So the method of undetermined coefficients, you multiply everything out, and then you need to set coefficients equal to each other on both sides. So in other words, first I'm going to look at the s squareds. Okay, there's an s squared here and an s squared here. There isn't one on the other side. So 0 for the first side, and then I'm going to have an a plus a c. Then I'm going to look at the s's. Okay, I have no s's on the left-hand side, and I have a b plus an a on the right-hand side. Then I'm going to look at the constants, and I have 10 on the left-hand side, and I have b plus 4c on the right-hand side. Okay, now we need to do some kind of substitution or elimination, some way to find a, b, and c. And so probably the easiest thing, I think I'm going to solve for c and b in terms of a using the first two equations and then sub them in the second. There's a lot of ways to do it, but if I just c is negative a and b is also negative a, so 10 equal negative a plus 4 times negative a. Okay, now I'm worried I messed something up because I don't think it's supposed to be a fraction. So, oh, it's not. That's negative 5. Okay, so that's negative 5a. So it looks like a is negative 2 because these combined is negative 5a. Okay, and so now I need to just say, well, then b, okay, in terms of a is just the negative, so it's 2, and c is also 2. All right. So I have all of the pieces, and now I need to go put them back up. Okay, let me double check. I want to make sure I didn't mess up a negative sign, because when I worked it before I got all 2's. So I want to make sure I don't have something wrong sign-wise. I think this looks right. So, okay, so let's go ahead and write down the left-hand side. And remember, I was just splitting up this first fraction here. So I've got a negative, let's see, negative 2 over, oh, I got the a and the b. So let's put them both together. So negative 2s plus 2 over s squared plus 4, and then I have plus 2 over s plus 1, and then I still have this plus 4s over s squared plus 4. All right, so I actually can combine these two guys because they have a common denominator, so let's do that. So 4s minus 2s is going to give me 2s, and when I do that, I'm going to go ahead and split the denominator now because that was one of our strategies, and then I'm going to have 2 over s squared plus 4, and then I'm going to still have that plus 2 over s plus 1. So what I did was I combined these two fractions and got 2s plus 2, but I went ahead and stuck the denominator under each piece, breaking it up into individual fractions here because that's how we're going to be able to inverse transform it. Okay, so now that's the work that you have to do in Laplace's world, and now that they're ready, we can just go ahead and bring them back. And so if we inverse transform y of s, we have y of t. Now let's inverse transform this thing I'm circling over here to the left. So I recognize that as an s over s squared plus 2 squared. So this is an s over s squared plus b squared. That's cosine. So the 2's out in front because it's just a constant that we'll just put on there. But then it's going to be cosine, and remember this is b squared here on the bottom, so it's going to be cosine of 2t. All right, let's move over to the middle term. I think I'll do each term in a different color since I got so much stuff going on the slide. You can see what we're doing. Okay, I recognize that one as a b over s squared plus b squared, and I don't even have to doctor it up because I need that b is 2 because the 4 is 2 squared. So that's perfect. That's just going to come back as a sine 2t. And then the last term, let's go ahead and do the last term. That one, I recognize that one as well. That's an exponential. So that's going to be plus 2 e to the negative, it's s minus a, so it's going to be negative 1. So that is my solution, and it makes some sense because our characteristic equation was x squared or r squared plus 4, which means r is plus or minus 2i. And remember, when we had the i's in there, that ended up giving us the sines and cosines with the 2 in front of the t. And then this last term that I wrote there in green is the particular solution with the a being found, and it's a 2 there. So it has that same form as if we'd have solved it the other way. Can I answer questions on any step there? Lots of steps. I'm going to do one more example, and then we need to talk about the multiplier rule extended, and then just a few more examples. So we've learned all we need to learn as far as solving, but we can't be done yet because you see already every time we did something, some new algebra thing cropped up. So I want to give you some examples that will help you with these.
I've got a question.
Okay, go ahead.
So, in blue in the middle on the right, after you had solved the partial fractions and you set up
right here. Is this where you mean?
Exactly.
Okay.
Exactly. So you added up those two common denominators.
Mm-hmm.
Negative 2s plus 2, and then the plus 4s.
Right.
And then got...
so that would have been 2s plus 2. I didn't write it because of room, but yep.
And then down when you figured out each
right here
each part of the solution, yes. Where did the plus 2 go?
Over here.
Right
so
here.
See, I split them up. So I stuck the s squared plus 4 under the 2s term, and that's my first one that's circled there. And then I stuck it under the 2 term, and that's the one that's boxed in red there.
Okay, I get it. Thank you.
Okay. Anybody else, any other questions? It's good to ask those things because sometimes I'm doing something and you're looking down, writing down. You look up and zoom, I'm halfway across the screen. So it's good to get it straight. Anything else before I leave that screen? Okay, let's do one more solving a higher order. And we want an example of that. And then I want to talk to you about the multiplier rule kind of extension, and anyway, a couple other things with our shifting theorem idea and some other things. So, okay, so here it is. Let's inverse transform it. Can I get you to mute your mics again because it's get that background noise?
Sorry.
That's okay. It's just crazy how any little noise just magnifies when you're in a group like this, so that's why I have to be picky. Not a problem though. I'm glad to have you talking to me. So, okay, so we've got y triple prime. So that's going to be s cubed Laplace transform of y minus decrease the s by 1 and start the initial values. This is what my head plays back, so I don't have that big old formula. Then decrease the s by another one and increase the initial value by a derivative. And then trying to fight the pen. Then take, and they're all subtract, and then decrease the s by another factor of s so it's gone, and increase the derivative by 1. So that's the pattern for whatever, order you're trying to take the derivative of. Now I still need, though, a y double prime, and here's the thing you got to watch out for. It's minus. And students will get the Laplace transform of the y double prime, but when they put the initial values in, they don't get that negative distributed. So we'll want to watch for that. So it's going to be minus s squared y of s, and then normally it would be minus s y of 0, but the negative distributes and makes that a plus. That was minus a minus. And then it's going to be minus y prime of 0, but same thing, that negative applies to the whole thing, and so that'll become a plus because it's minus a minus. Okay, now I'm going to have to put this on the second row. I've only done the first two. Okay, so now I've got minus y prime, so that's going to be minus s y of s, and then minus y of 0, but again, because it was a minus, I need to make that a plus. It's another minus a minus. And then finally on the end is a Laplace transform of y. So that's the whole left-hand side in a row and a half there, equals 6 over s minus 1, Laplace transforming that exponential. Okay, one of the things I really like about this problem is these guys are all 0. Okay, every one of these initial values. At 0, everything is 0. So that's going to actually get rid of all these guys. So had you not, whoops, let's see, yeah, I got that right. Had you not remember to change the signs, you would have gotten away with it here. But all of those are going to 0 out because all of those initial values are 0. So let's figure out what we got left. We've got x cubed minus s squared minus s plus 1 on the y of s's. So I just grouped all of the terms, factored the y of s out, equals 6 over s minus 1. Okay, so now I'm going to need to divide by this thing right here, but I also am going to factor it, and I think I'll factor it first while I've got it over there and got a little bit of room. It's 4 terms, so I'm going to factor by grouping. I'm going to factor out the s squared in the first term, and then the factor by grouping, you want the factors to match, and there's nothing to factor out here except I want it to be an s minus 1, so I'm going to factor out a negative, and really it's a negative 1. That will change the signs here, so some more algebra to remember. And then the s minus 1 is in common, so I can factor it out in front, and that'll leave me s squared minus 1. So the factor by grouping, this is how that factored. Okay, now I'm ready to get the y of s by itself. I'm going to write it up here just in the interest of screen room. And so, whoops, and so I'll have 6 over s, and actually let's take this and let's factor it some more into s plus 1, s minus 1. So what's going to happen is I have the s minus 1 that was already there, and I've got another one here and another one here, so it's going to be s minus 1 cubed and then s plus 1. Okay, so that's my getting the y of s by itself. This is going to need partial fractions, and it's going to need something from partial fractions that you may not have remembered. That's why I'm trying to do examples of each type of thing that can come up in Laplace's world when you're trying to get these in a form to get them back. Okay, when you set up partial fractions, you are trying to set up any possible fractions that when they're combined gives you that, combined fraction. So if I was setting this up, and I'd have 6 over s minus 1 cubed and s plus 1, well, there could have been a fraction with a s minus 1 cubed on it, but there also could have been a fraction with an s minus 1 squared on it, because if you ask me for the common denominator between those two I just wrote down, it's x minus 1 cubed. That's the common. You'd leave a by itself and you'd multiply b by s minus 1 top and bottom, and you'd have a common denominator. So that's a possibility. But There's another possibility. There could have been an s minus 1, because if I asked for the common denominator between all those three, it's s minus 1 cubed, but there could have been lower powered fractions in there. So that's one of the rules of partial fractions. If your factor in the denominator is raised to a power, you have to have a fraction for each lower power too, because when you get the common denominator, you know, those could have been in there and you don't see it as such over here once it's combined. Now I still need one more for that last factor. So this is called the repeated factor, and you've got to have one for each lower power. And then we're going to solve it doing the partial fraction stuff and see what happens, whether we do need the b and the c. So when you clear to fractions, just a minute, what happened here? Oh, it flipped back. Sorry, I'm getting, there we go. Okay, so when you clear to fractions, you have 6 equal a. Now the a, you're multiplying everything by this common denominator. And so the s minus 3 cubes will cancel, and that'll give you an s plus 1. And then plus b. Now what happens on the b, if you multiplied b by s minus 1 cubed and s plus 1, the squareds will get rid of 2 of those, but it'll still leave one of them. So this is going to need an s minus 1. So the cubed left that, you know, canceled with the bottom, so it left one of those and an s plus 1. Now on the c, if you did s minus 1 cubed s plus 1, that pen's annoying. I've got to do some troubleshooting today. Okay, so sorry, s plus 1. This s minus 1 will get rid of one of these and leave 2 of them. So this is going to be s minus 1 squared and s plus 1. And then finally plus d. And the s plus 1's cancel and leaves you s minus 1 cubed. Okay, so that's what the partial fraction things look like when you've cleared it of fractions. Now you can conveniently pick -1 and you can find the d, and I then conveniently also picked, you can pick +1 and you can find a, and then I just chose other numbers to plug in. So I put the a and the d in that I found, and then I let s be 0 and I let s be, I don't know what else I chose, but you can let s be whatever to find those, and I decided that was easier than multiplying it all out. So you are able to find this, and if you want, I mean, I can write it all out, but I think in the interest of time right now, I'm just going to show you what I ended up getting, which was this. And it turned out it did need all of those fractions. Every one of them I found something for. So I easily found a and d by our convenient method, and then I plugged in those a and d numbers, and I let s be 0, and I got an equation in b and c, and then I let s be, I probably used a 2, I did, and I got another equation in b and c and solved it for b and c, and this is what I got. So it was messy because it was fractions and it was huge, but it was just algebra. Okay, so now that we're at this point, though, that was the hard stuff. We're ready to come back into our world and inverse transform it. We can do it a term at a time. We've got a couple things going on here. So the first thing is we got y of t on the left hand side. Okay, this one involves the first shifting theorem. Remember when you have s shifted, okay, so it's shifted because of that -1, it shifted 1. That means there was an exponential in there. And so you do the exponential part, then you cancel the shift, and then you inverse transform the rest. So this is going to be e to the something times something else. I'm going to move this down a little because I didn't leave myself enough room. Okay, so it's y of t equals 3. Okay, I'm going to put the 3 on there because that's, well, maybe I'll forget the 3 for a minute. Let's just do the shift because we may need the 3 in part of the inverse transform. So this is going to have an e to the t on it because of this shift. Whatever this shift is, it's minus, and then whatever the number is, it's like the s minus a thing. So it's a positive 1, so this is going to be e to the t. Now I'm going to cross the shift off. The shift in Laplace's world meant an exponential in our world, and I've got it. Now I'm left with 3 over s cubed to inverse transform. Okay, when I'm thinking of trying to inverse transform and I've got the 3 over s cubed, well, I'm thinking of the inverse transform, and that needed a 2. Well, I don't have a 2. I have a 3. So I'm going to put a 2 in there, and then I'm going to compensate for the fact I put the 2 in there. So now I can inverse transform this piece without the shift, and it's 2 over s cubed. So that will come back as a t squared. I'm going to write it in front, just like how we usually write solutions. So this comes back as a t squared, but then I also have in front a 3 and a 1/2, so 3 halves. Sorry, that squished. Let me slide this over. Okay, so does everybody see where we got that one back? The shift meant the exponential, and then I needed 2 over s cubed. That's the Laplace transform of t squared. So I put the 2 in. That came back as the t squared. So then I have the 3 halves. All right, let's move over to the next term then. So I have a minus between them. I've got a shift going on again. So that tells me e to the t again. Then I'm going to cross out the shift. And so what I have is an s squared and a 3 halves. Well, I know s squared needs a 1. So I can just put the 3 halves as a constant out in front. Just a constant later, so there it is. And then I inverse transform. If I move the 3 halves left, I have 1 over s squared, and that comes back as a t. Okay, then we're going to move over to the next term, and that's just 3/4, and the 1 over s minus 1, that's just e to the t. Well, this all looks really familiar, because if I would have had to do integration by parts or tabular on something, this is the type of solution it ends up being, and that's what would have happened had we tried to solve it the other way. Okay, so now let's do the last piece right here. This last piece is negative 3/4. And then, oh, there's the shift. No, I don't need, I mean, it just comes back. It's a shift. You can think of it as a shift. It'll be an exponential, but it'll just leave us at 1 if we did that. So we know 1 over s minus a comes back as an exponential. So this is e to the negative t. Okay, so all of this stuff is the solution. And just so I can see if you've got it, can you recognize for me which of this is y of h and which of this is y of particular solution? We didn't factor and solve the characteristic polynomial here, but you shouldn't need to do that. We know that our particular needs to be an e to the t, but look at all those e to the t's in there. Well, the particular one then must have been this one, because remember, if it's a repeat and solves the homogeneous, that you need a factor of t, and if it repeats again, then you need another factor of t. So all of this stuff was the y sub h, and so it looks like our roots on this, so we have the e to the t's in there, but it was repeated twice, so we needed the t e to the t and the e to the t, and then the other root was a negative 1. So the roots would have been 1, 1, and negative 1 there, and that was the homogeneous piece. Since the particular solution repeated the two different terms of the homogeneous, it needed the t squared. So this one would have been crazy to do kind of either way. It's just a big problem, but it's good to see because I had a lot of important stuff to see in that. Any question on anything before I leave this one? Okay, a few things to point out then. We had what was called the multiplier rule, and one of you asked me this week a good question. How do you do the multiplier rule in reverse when you're inverse transforming? Because the multiplier rule made us take a derivative, and like, how would you ever see that to undo it? And you wouldn't, but it'll come back in other ways. The reason why is you do the multiplier rule and you get it transformed, but then by the time you solve for y of s and you divide that over and your partial fraction and all of that, it's going to look different anyway. So you don't ever try and undo the multiplier rule by looking for it in Laplace's world. So that's not going to be an issue. But if you remember what the multiplier rule was, the multiplier rule said if you have t times a function and you need to transform it, you can transform the function, that's what this part is, and then you can take the derivative with respect to s of that transform, but you need to change the sign. Okay, we derived it and saw last time where that came from. Well, that turns out that generalizes to higher order as well, higher factors, powers of t, and so I wanted to point that out. So we did this one. This was the way we got it before, as we applied the definition, and then we saw that if you did a derivative, that would generate a negative s. So the negative made it positive if we put a negative out in front of here. So I mean, that we came up with that last time, but what if we tried it with a t to the n? So if it was a t squared or a t cubed or something, how would this rule work? And that's what we're interested in seeing. Well, what ends up happening if you integrate this, you end up getting this, or yeah, let's see. How do I undo this? Now, if you take a derivative of this, you end up getting negative s. If you take the second derivative, so negative s e to the minus st. If you take the second derivative, okay, of that, you have an e to the minus st. Now you get an s squared, and now it's positive because you had a negative and a negative. If you did a third derivative of this, then you would have an s cubed, and it's going to be negative again. So if you were taking derivatives, every time you took a derivative, you generate another s, and you also change the sign. And so how the multiplier is going to work, we're going to have a negative 1 to the n. That will handle the sign change part. If it's a 1, if it was t to the 1, then it would be a negative, which is what we need. If it's a t squared, it'll be a 2 there, and then it'll be a positive on the s squared. So you will take the derivative n times, and so it's just analogous to what we had up here. Let's see, where do we have it? Up here, except we needed to handle that negative 1 at the end because it's going to be changing signs. And then the derivative can come out in front, and then this is just the Laplace transform right here. So bottom line, if you have a t to the n times a function, you can transform it by doing negative 1 to the n. That'll take care of whether the sign needs to be positive or negative. And then you need to take the derivative of the Laplace transform that you get n times. So you'll transform whatever it is, and say once you transform it, you get 1 over s squared or something. Then that's t, so you wouldn't get that, but you get something. And then you take a derivative of that as many times as whatever the power was on the t. So that's called the multiplier rule extended, and it just gives you a little more in your toolbox for transforming right hand sides. That could have been like a t squared function of some others, t squared sine t, or a t to the 4th cosine t, or a t to the 5th e to the 3t, or something like that, and this would be how you do it. Then one more thing to point out, if we wanted to Laplace transform this, well, let's go ahead and use the multiplier rule. so we can see how to do it. So this is where the n is a 2, and so we're going to transform that. So this becomes, whoops, why'd that go away? This becomes g of s, because it was g of t, and we're going to Laplace's world. And so what we're going to do is we're going to put the 2 out in front, because let's can do that later because it's linear. And then we see the t squared, so we're going to do that with the multiplier rule with the n being 2. And so we'll do that in a minute. So what we have to do is Laplace transform this piece, and then we'll need to take 2 derivatives of it. All right, so let's Laplace transform. Oh, let's handle the -1. I forgot to mention that, but that's going to disappear because it's t squared. All right, so now let's Laplace transform e to the t, but then we're going to need to take the second derivative of it. Okay, so the Laplace transform of e to the -3t is 1 over s plus 3, because it's s minus a, and a is 3, a -3, so it makes that a plus in the end. Okay, so now I need to take the derivative of that twice, and then I will have the Laplace transform. So let's do the derivative. Let's see, that's just still going to be a 2. So we're going to do another derivative in a minute, but let's do the first derivative. I'm going to think of this as s plus 3 to the -1. Okay, so power out in front, decrease the power by 1, so this is going to look like this. Or it's going to be negative s plus 3 to the -2. So I can do one more derivative of that. And one more derivative of that is going to be power out in front, so that'll now make that a 4. And then decrease the power by 1, so over s plus 3 to the 3rd. So that's how the multiplier rule works, is you do that -1 to the end, take the Laplace transform, and then do however many derivatives that power on the t was. Any questions on how I got that? Well, what if, remember we learned the first shifting theorem. We learned basically if there was an e to the something times a function, that you take the Laplace transform of the function and then you shift it. Well, that would have applied here as well. So I was looking at this as e to the something times a power of t, and that used this multiplier rule. But I could have looked at this as a function of t and with an e on there. So let's do it that way and see what happens. Okay, so what I need to do is I need to Laplace transform 2 over t squared. And so remember what that is when we Laplace transform t squared. So 1 over s was 1, 1 over s squared was t, and t squared was 2 over s cubed. Okay, so I have the 2 still, and then Laplace transform is going to be 2 over s cubed. However, it has multiplied by the exponential, so I need to take the s and I need to shift it. So this was s cubed, but I need to shift it, and so it's going to be s minus a -3, which is s plus 3. Well, look, we got it both ways, and I think the shifting theorem was definitely easier. But bottom line, the important thing to see here is they both work. So, you know, if you see this and say, okay, it's a t to a power and a function, and you use the multiplier rule, it works. If you say, oh, this is a function of t and an exponential, you can use the shifting theorem, and it works. Because, I mean, they both give us equivalent things. So I just wanted to point that out, because I'll have students ask that, say, well, should I use that it has the e in there, or should I use it has the t to the power in there? And the bottom line, they both work. I think the shifting theorem's easier in most cases. Any questions on that? Okay, my plan then is I've got two more differential equations because my goal here is to have you see enough of them that when you're working on the homework you go, okay, I remember all the algebra and all the things that might come up. So let's do another one. Let's transform one that's right hand side. We only did exponentials. Let's do a trig function because that's very common. This could be a model for a spring mass system that you hooked on a driving force to drive the spring following this a cosine thing, you know, it would up and down kind of thing. So this would be a legitimate model. Let's see if we can go ahead and solve it with Laplace transforms then. So it's going to be s squared Laplace transform of y minus s first initial value minus initial value at the derivative. So there's my y prime, double prime, sorry. And then I've got 16 times the Laplace transform. And then over here on the cosine, I need to Laplace transform cosine. So I know that's s over s squared plus whatever's in front of the cosine squared, so 1. Let's go ahead and put in our initial values. Y of 0 is 0, so that one's gone. This one's a 1. Alright, so we're going to get ready to solve it for y of s. So we're going to factor out the y of s. So s squared plus 16 y of s equal s over s squared plus 1 plus 1. So I had to move that initial value over to the other side. Alright, so now let's divide by the s squared plus 16. I'm going to just cross it off here and write s squared plus 16 right here and s squared plus 16 right there. Alright, so I have solved it for y of s. Now in looking at this one, it's going to involve partial fractions on the one side and the other one has that same denominator as part of it. I think I'm going to combine it first. Now you saw one example I combined the fractions and then did the partial fractions. Another example I left them split. Sometimes it doesn't matter, but I wouldn't have to do partial fractions twice on this, so I could leave it, but I think I'm going to combine it because I got those quadratics in there and I just think in the end it's probably going to be easier. So what I'm going to do is I'm going to multiply this by s squared plus 1 top and bottom to get a common denominator. Alright, so my right hand side is now s squared plus s plus 1, just adding all the tops, and then I've got s squared plus 16 and s squared plus 1. Okay, partial fractions. Not going to be fun because both denominators are quadratics that won't factor, so both numerators are going to need two terms. Okay, so I'm going to have s squared plus s plus 1 over s squared plus 16 s squared plus 1. So I'm going to need an as plus b. Because of the quadratic factor in the denominator, there could have been an s term in the numerator. And then I'm going to need a cs plus d because of the quadratic again there. Okay, then I'm going to clear it of fractions. So that would cancel here, and the s squared plus the 16 will cancel and leave me an s squared plus 1 here. And the s squared plus 1 will cancel and leave me an s squared plus 16 here when I clear them of fractions. Okay, this particular one I think is just going to be easiest because there's nothing that's going to zero out with these, is to just multiply it out and equate coefficients. So that's what we're going to do next. So I'm going to have s squared plus s plus 1 equals, I got a FOIL, so as cubed plus bs squared plus as plus b, and then plus the second one cs cubed plus ds squared plus 16cs plus 16d. So it's big and it's long, but it is just algebra. So let's go ahead now and we'll equate coefficients. So we're going to look at the s cubed terms. There's none on the left. There's one there and one there. So going to be a plus c. Then let's look at the s squared terms. There's one on the left, and that leaves me a b plus a d on the right. All right, so now let's look at the s terms. Okay, there's one on the left, there's a and there's a plus 16c on the right. So I'm generating, I have four equations and four unknowns, but they're all fairly simple, so that part's good. So now I'm going to look at the constants. Okay, there's one on the left, so constants are things without s's. This is the stuff that's left. There's a 1 here. There's a b plus a 16d. So now I have a bunch of equations and a bunch of unknowns, but they're all, pretty simple. So let's see. Let's look at, let me just get, sorry. Let me just get it. Man, I'm having troubles today here. Let's see. Where did we go? Right here. Okay. So let's see what I'm going to do. So I think we've got this equation, a equals negative c. So let's go ahead and put that in over here. So I have 1 equals negative c, that's what a was, plus 16c. So that's 15c. So c is going to be 1/15. Okay, so solving 15c, divide by 15. Now let's do the b's and d's. We're going to do kind of a similar thing. Let's solve this simpler one. Let's find out what b is. B equals 1 minus d. So we'll put that in right here. 1 equal 1 minus d plus 16d. Okay, so that looks like 15d, but we move it over as 1, so d is going to be 0. All right, well, if d is 0, then b is going to be 1. Okay, so let's see what we've got here. We got b and d and c, and I didn't write down a, but the connection is a is minus c, so a equals 1/15. Okay, so it's doable. Now I need to go put those back up in the pieces up at the top, and I think I had them in the other order. I wrote the s squared plus 1 when I worked it on my paper, and so I put the partial fraction numbers back in on the next slide because I knew I would be out of room on this slide to keep going. So let's take those values, the 1/15 for the a and the c and the 0 for the b and the d, and this is what it ends up looking like. Now I've got the two fractions turned around, so you can turn them around or whatever, but those are the things we just found. And so now, can we inverse transform it is the question. We kind of had done the work, and really it's not going to be too much work. The partial fraction was work, but I can do this one right now. So let's see what we've got. We've got y of t equals, put the 1/15 out of the way. So the 1/15 can just go on later because it's linear, and let's just look at this guy. Well, I recognize that guy, right? That is just cosine, and it's a 1 squared, so it's just cosine t. Okay, now this one is the one I'm going to want to split up. So I'm going to have 1/15 s over s squared plus 16 plus 1 over s squared plus 16. So anytime you have two terms in the numerator, you're going to want to split them. And so this one, I can already see what it is. I've got a minus 1/15 out in front. And s over s squared plus 16 is going to come back also as a cosine, but this time it's going to be a 4t because this is b squared, 4 squared. Okay, looking at the last one, to bring it back, it doesn't have an s on top, so it needs a b on top, and it doesn't have it. B, I was going to write b, but b needs to be 4 because this is 4 squared. And so then I need to compensate for the fact that I stuck a 4 on. Now this part will come back as a sign, and it's going to have a 1/4 in front of it. So the partial fraction stuff was kind of big and ugly, but once we got it broken down, the coming back was pretty easy. Any question on anything I did? I can go back to the last slide or anything on this slide. Okay, so each of those we've kind of seen different things that might happen in them, and so I just wanted to give you, like I said, several kind of for reference. I actually got to do one more because I haven't done today one of the ones that is commonly required, and that's a complete the square. And I just pulled this one off the assignment page because I thought, oh, this one's a little bit tricky, and I just wanted to let you have an example of sort of the algebra that's going to be involved to get it ready to inverse transform. So we've just got a few minutes, but I think we'll have enough to get it there, and at least to show you the part I want to show you because it happens a fair amount. Okay, so we've got s squared y of s minus s y of 0 minus y prime of 0. That's our y double prime. Then we have plus s y of s minus y of 0. That's our Laplace transform of y prime. And then we have plus y of s. That's our Laplace transform of y equals, and we got a Laplace transform 1. That's 1 over s. Okay, so we've got it transformed. We're going to put in the initial values. Oh, nice. Okay, that's 0, that's 0, that's 0. So that makes it a little better. So I have s squared plus s plus 1 on the y of s equals 1 over s. So we can get y alone now by dividing by that stuff. So the y of s alone. So it's going to be 1 over s times s squared plus s plus 1. Okay. This then is going to need partial fractions, and then it's also going to need something else in a minute. So that's why I wanted to do this as an example. So let's do the partial fractions. I'm going to do it down at the bottom again, I think. So I'm going to have 1 over s times s squared plus s plus 1 equals a over s plus bs plus c over s squared plus s plus 1. Always need that s term in the numerator if the denominator is quadratic and doesn't factor. Alright, so clearing it of fractions, I'll have 1 equal, I'm going to go ahead and do the multiplication while I'm clearing it. So this was a times s squared plus s plus 1. So I'm going to distribute that through as squared plus as plus a. So just multiplying that through, and then this one just needs that s on it, so plus bs squared plus cs. Okay, so we're going to equate coefficients. Looking at the s squareds, I have none, and I have a plus b. Looking at the s's, I have none, and then I have a plus c. Looking at the constants, I have 1, and I have a. All right, good. I got a. Well, that's going to be real easy to find the other two then, because a plus c is 1, so c must be negative 1. And then b also must be negative 1. So in this case, the partial fractions weren't too bad. Okay, so let's go ahead and write down our y of s. It's going to be, a was 1, so it's going to be 1 over s, and b was negative 1. So it's going to be, well, let me just put it, I'll just put it combined, and then I'm going to end up splitting it. So it's going to be negative s minus 1 over s squared plus s plus 1. Okay, so that's what it looks like now. And this one, I got it. That'll come back as a 1. So that's going to be easy, that part. But this other part has two terms, so I would want to split it into negative s, I'm splitting it into negative s over s squared. And actually, before I split it, because I want to write it so it's ready to go when I do. This one, I am going to want to, this is an s, I want to complete the square on it because I want to be able to express it as s squared plus b squared, and it's actually going to be expressed as s plus some a squared plus b squared when I'm done. It's going to have a shift in it, so we'll have an exponential, but then it's also going to come back as a trig function, but I can't see that unless I have it as some stuff squared. So I need to complete the square on that denominator. Well, the problem with that is it doesn't complete the square nice little integers, but that's okay, it still works. So this is where we want to complete the square. S squared plus s. So to complete the square, plus 1. Okay, so we're going to move the 1 over, just kind of out of the way. To complete the square here, we need to put in the number that is half the middle squared. Well, the middle is 1, half the middle is a half, squared is 1/4. So I put 1/4 there, and so I have to compensate for that fact that I added a 1/4, so I'd put minus 1/4 over here. So this denominator will factor into s plus 1/2 squared. If you FOILed that, you would get this guy, and then plus 3/4, because this guy combined 1 minus 1/4, 3/4. So that's what I'm going to write over here. X plus 1/2 squared plus 3/4. That's one of the denominators. I'm splitting this up, so then minus 1 over the same thing, s plus 1/2 squared plus 3/4. Pretty ugly, but I wanted to give you an example. If you got to complete the square, if you have a quadratic that has all three terms, you're going to take the first two, complete the square on it, so you can get it as a s plus a quantity squared, and then a number on the end. Okay, I finally have it broken down then into what I need for the partial fractions. So, okay, so this was s plus 1/2 squared, and I'm going to write, and this was 3/4, and that is square root of 3 over 2 squared is the 3/4. So that's going to help when we need to bring it back. So this is s plus 1/2 squared plus square root of 3 over 2 squared. Then we can clearly see what our b is as well. All right, then I need to have the shift. So this has to have a shift on it, and you can't bring it back if you don't have the shift on it, so I need to put that on there, but I can't just stick a plus half on unless I compensate for it. But I'm going to put the minus 1/2 over here because it would just be the same kind of denominator as over there, so I can combine those. So that stuff in red is to get the shift taken care of. Now I can bring back those first two terms, and then I got to doctor up the last term in a minute. So y of t going to come back as still a 1. The shift is going to be an e to the minus 1/2 t. That takes care of the shift part. Then I have the s over s squared plus b squared, so that becomes the cosine of square root of 3 over 2 is the b t. Okay, so that takes care of that part now because I had the shift in there, and that term ends up being the same thing I had before, but this piece would have been lost because I need to have those shifts match. So now I'm going to go over to the third term, and so this is minus 3/2. I'm just going to combine those two. Alright, so the first thing on there is it's got the shift, and I think I'm just going to go ahead and put the minus 3/2 here. And so I do the shift, which is e to the minus 1/2 t, and that took care of the shift part, but I still have the s squared plus b squared, so I need b on the top, and it's not there, so I have to put it there. But if I put it there, I've also got to compensate for it. Okay, so this part, because now I have the b on the top, will come back as a sine. So it's going to be sine, and it's going to be square root 3 over 2t. But then I have that 2 over square root of 3 that goes on here as well. Let me move that over so it's not crashing into each other. So I had the minus 3 over 2, but I also have a 2 over square root 3, and those will cancel. So final answer, 1 plus e to the minus 1/2 t, and you can leave it there, but I think I'm going to factor it out. So cosine square root 3 over 2t, and then minus 3 over square root 3 sine square root 3 over 2t. That's kind of the way we're used to seeing those answers listed. That is the correct answer. I just messed up in my hurry, and maybe it's good I did just so it's pointed out so you guys can watch for it.